This is a bathroom terror detector with Raspberry Pi 4, and I implemented MobilenetV2, YoloV8, YoloV9, Yolo World, and Siamese Network to try to get the best optimal solution to see if I could detect the bathroom terror, which we'll get to in a bit. I had to pause on this to move across the country to beautiful upstate New York, but YoloV10 and 11 came out, so I'm now going to be adding those in to compare as well. So I'm going to explain what I made and why, how I integrated the sensors, and then we're going to be jumping into the machine learning algorithms, how each of the algorithms work, how I integrated them, and stick around to the end if you want to see which one worked best and why. And a big thank you to the sponsor of this video, Storyblocks. So I'm working on this class, Intro to Raspberry Pi, Sensor Processing Python for the Makerspace, which is a really creative space in Salt Lake where you can do woodworking, metalworking, CNC, 3D printing, all sorts of things. My setup is I have a Raspberry Pi 4 with this 32 gig micro SD card, which I've already loaded and pre-installed Raspbian on. I have a USB-C for power. I have a micro HDMI for the monitor connection. I have a USB connecting over Bluetooth, my mouse and keyboard. I have an RGB connecting RGB and ground over the GPIO pins. I have two connections for ground and reading for this open door close sensor. And I have this camera port connection to an RGCam no IR camera, and I have a no IR camera because my original plan was to piggyback off of this tutorial that was already existing using a no IR camera to be able to detect the health in plants. Normally cameras will filter out all of the IR data, and that way it looks normal to the human eye. But if you want to be able to detect plant health, then if you keep the IR data, then how much IR data is being reflected will be indicative of how healthy the plant is. After implementing it, I realized that I would then have to be carrying in a plant every time I had that class, and looking back to when I was in the Marine Corps, I had a roommate who was a former nun, and she had given me this adorable little bamboo plant that's supposed to be unkillable. Somehow I managed to kill it, so I decided to move on. I thought maybe instead I would do like this security classifier where you could use sensors, be able to detect when there's a person, and add a few more sensors to make it interesting. What's really nice is this is actually a full computer in itself. When you add all the accessories, then you can just boot it up like any normal computer running Linux. So what are the use cases for this class or project? Well, we have the security systems. You detect if somebody is in the vicinity or if the door is opening and closing and you have some type of alarm. The other use case could be a delivery bot where you have to verify with camera that it is the person that you want to deliver it to. You open the doors, and then once you detect that the doors are closed again, then you can lock and latch and move on. So the third case you'd really only think about if you've ever been through it, and that would be the bathroom terror. So let me explain. I have a 3-year-old that has been doing amazing at potty training. He's been going to the bathroom, but I've been noticing some of the time he spends a little bit too much time in the bathroom. And I start wondering why, and when I go to investigate, I start finding this, and this, and this, and this, and this, and this, and finally this. And I mean, you can only be so mad at him because the very last one, like, he was trying to wash his tablet so it could be cleaner, and he just didn't understand that water might destroy it completely. So I thought maybe if I added an audio component to this, then I would be able to leverage the system to be able to detect and kind of alert me before or when he goes to the bathroom, so that I could be ready to monitor and deflect before terror ensues. It is amazing what kind of terror and chaos 3-year-olds can cause in like 30 seconds. So the first step is to get the LED working. I'm just going to have the LEDs blink once for red, twice for green, and 3 times for blue, just to make sure that we're connecting the right pins to the right colors and it all works. We're going to create our repo locally. Let's create the files that we're going to use to put the code in, and then create a branch so that we can start with the LED. We've connected the GPIO pins to 27, 17, and 22 for red, green, and blue, and then also to ground. And we're using the BCM pin reading mode, which tells us which numbers to associate for the pins. First, we import necessary libraries, then create global variables for each of the LED pins, then create a clear LED function to turn all of them off at once, then create a control LED function to turn on or off a certain color, Then create a clear function to show a break in between clearing the LEDs. Then in the main loop, we set the GPIO reading mode to BCM. Then we set each of the LED GPIO modes to out. Then in the while true, we continuously turn on red once, blue twice, and green 3 times. Okay, great, it works. So let's create an LED branch, then add our file to be staged in our working directory, then commit it. We'll go ahead and check out master and then merge the LED branch into master. So now we're going to program the open door close sensor, and we've connected the pins to 16 for the information reading and ground. And so we're just going to turn the LED red if the door is open and then green if the door is closed. Let's create a new file test door for the code and check out a new branch called door. A lot of the code in this program is the same, like reading in library, setting the RGB GPIO pins, the clear LED, control LED, and clear function, setting the GPIO mode to BCM, and setting the RGB to outbound mode so we can control it. But now we need to set the door sensor GPIO pin, and we have a door is open function which reads in the door state and returns true if open and false if closed. We set the GPIO mode for the door sensor to in so we can read it. In the while true loop, we check is the door open, and if it is, then we set the LED to red, and if it's not, then we set the LED to green. Now test. And it works. We add the test store file to be staged, then we commit it, go ahead and check out master, and we merge the door branch into master. Next, for the human detector. So I got to admit, I spent way too long on the installations, probably several days, just getting everything to work together to actually get the dependencies and libraries installed, like OpenCV, PyTorch, ton of other dependencies. After a few choice words, I got through all the bugs and issues, like not allowing pip installs because they wanted to have control over certain packages, and I got it to work. If you want to avoid this headache, I'm offering the image file with all the pre-installed libraries for free to anyone who wants to join my Patreon, where you can become part of my network, see what I'm going to be working on next, get insights into the backstory of my projects, get useful tips and tricks, and tell me what you're interested in. Also, anyone could go to my website to see all the hardware that I've used for this project in case you want to be able to build it yourself. So, first let's get the pipeline working for the camera. Let's create a test camera Python file and check out a camera branch. First, we import libraries, then we create the camera manager object, then we have the init function, which is the constructor. It happens automatically when the camera manager is initialized. Inside, we initialize the PyCam2 object and call the start function. Then we have the start streaming function. We have a try except, which cleanly closes if any errors happen, and in the while true loop, we capture the image frame each time from the main source of the PyCam2 object. Then we use OpenCV to display the image, and we handle Control-C if run in the program. Then in the if name equals main, the main entry point of the program, we create a camera manager object, and we call the start streaming function to get the data flowing. Let's add the test camera file to be staged, then commit it, and then we'll check out master, and then merge the camera branch. Next, the detector. So I implemented MobilenetV2 to begin with because I saw somebody else had a tutorial on it, and I saw, okay, this works on a Raspberry Pi, which is a constrained hardware system, so it's often easier to start with something you know already works. But they were detecting something else, like fruit and different things within their room. So let's take a quick step back and recognize what are the steps in actually training a machine learning model. First, collect, clean, and label the data, then create a model, then train the model, then evaluate, then test on brand new data, then export, then integrate into your algorithm, then deploy. And if you're using a pre-trained model, which is what we're starting out with, you're just going to jump all the way to this step. We're going to create a project folder to hold our MobileNet implementation and CD into that folder. We're going to create the MobilenetV2 file and a main Python file. And let's check out a MobileNet branch. So what is the MobilenetV2 algorithm? It's a classification algorithm that was specifically written to help reduce computation and memory for constrained systems, like a mobile phone, hence MobileNet, or in our case, Raspberry Pi. So the sequences, they have a convolution, batch normalization, and ReLU before and after a series of residual bottleneck layers. I read 19 in the paper, I saw 17 in the code, but it doesn't really matter. And then they have adaptive average pooling, then linear classifier head, which tells the network what you're actually looking for to classify. They use 3x3 kernels and dropout. The innovative piece of this is the residual bottleneck layers. So what are those? The first thing we need to look at is the depthwise separable convolution. This was something that was used in MobilenetV1 and other algorithms. The concept is that you can take a full convolutional layer and break it up into a depthwise convolution, the 3x3 kernel, and the pointwise convolution, 1x1 by some depth, and that can significantly reduce the computation by a matter of k squared or a little under that. So if you have a 3x3 kernel, you can reduce it by 8 or 9 times, which is significant. Next, we need to look at manifold of interest for the linear bottleneck. So when we send the low-dimensional feature map in, which are features that we're getting from the image, we do pointwise convolution, which expands the dimensions, so we're able to do nonlinear activation with ReLU, and then perform depthwise convolution, ReLU again, and reduce the dimensionality back with pointwise convolution 1x1, and then we perform the linear activation. So why do we have this expansion and reduction of dimensionality when we're performing these operations? Well, the idea is we want to just focus on the manifold of interest. And we have a manifold of interest because when you look at the image that gets sent through, we wouldn't actually send any image through, right? So let's look at what is an image. So an image is a series of pixels of a certain width and height where each pixel has a red, green, and blue value between the values of 0 and 255. And if you think of all of the possible images that could be created, each pixel could be any value between 0 and 255 for each red, green, and blue. There's a massive number of images that could be created with this variation. And so if we look at this, we have a house that looks like a real image. We can interpret it, it's understandable, but just as easily we could have this black and white blob, which means absolutely nothing, right? So the manifold of interest is really focusing on the output that's been sent through the low-dimensional feature map and through convolution and ReLU that's representing images of things that we actually care about sending through. We're reducing the dimensionality to the manifold of interest, which only represents the images that we would actually care about sending through. So the final thing we want to look at is ReLU is a nonlinear activation function, which we're able to do once we've expanded the dimensionality, and that helps improve the complexity for the model to be able to learn nonlinear information and improve its performance. But when we reduce the dimensionality, it would lose more data than we want to actually lose by performing ReLU, so instead we perform a linear activation at the end of the residual bottleneck layer. And a residual connection is added between the 2 pointwise convolutions, which are at the same dimensionality at the beginning and at the end, and that helps improve the gradient flow for backpropagation. Let's go ahead and look at the MobilenetV2 code, which is based off of the camera streaming code that we looked at before. So first let's import libraries, then we'll create a camera manager object. Then inside of the init function, we set the PyTorch quantize engine to QNNPack, which allows running the model on an ARM-based system, which is what the Raspberry Pi is. Then we create a PyCamera2 object and start the data streaming. Then we'll create a preprocess member variable that allows transforming each of the image frames to a normalized tensor. Then we're going to create a MobilenetV2 model based on a pre-trained network, and we're going to allow it to be quantized. And so that might have a slight reduction in precision, but because we're allowing the tensor operations to be done based on int8 values rather than floating point values, we have a more compact model. We're taking up less space in memory, and that allows for a higher performance in vector operations during inference. Then we go ahead and convert the model to TorchScript, which is a subset of Python, and that both allows for the model to be serializable, which enables you to later export it and run your model outside of Python in something like a C++ module, and it allows it to be compilable, which enables different performance and optimization improvements. Then we go ahead and loop through the ImageNet classes from the text file that I've downloaded from this website that PyTorch recommends for ImageNet classes and save it to the categories member variable. Then in the start streaming function, we have a try except, which handles any errors cleanly. I use the with torch.nograd because we're not updating the gradients, and then in the while true loop, I capture the image frame, just the first 3 channels, and I pre-process to make it a normalized tensor. I unsqueeze so that it's in a mini batch format of just 1 sample, and then I send the data through the MobilenetV2 model, And then I capture all of the probabilities by using softmax, and because it's softmax, they all have to add up to 1, and with ImageNet, that's 1,000 probabilities. So you can imagine a lot of them end up being 0.00 whatever. But we're just going to capture the top 3 with their categories, and then loop through them and print them out to see which do we have the highest confidence in classifying. Next, we display the image so that we can see it streaming, and we handle any Control-C cleanly. And then finally, we're going to have this in a separate file in a main.py. We have the from MobilenetV2, which all the other code is in a MobilenetV2.py. We import the camera manager, and then in the if name equals main, we create a camera manager object, and then we call the start streaming to get the data flowing. So I got MobilenetV2 working. So I can see I'm being classified most commonly as velvet, sweatshirt, and jersey. Velvet at like a 10 to 12%. So why am I not being classified as a person or a human? And I started looking into why am I not being detected? And there was 1,000 different classes because it was pre-trained on ImageNet. And I started searching through those classes and I could not find human. And I realized I was an idiot for not like even thinking to check through the classes and see, okay, is human in there? And I grepped it and it wasn't in there. So yeah, I started looking through some of the other classes and what? A bittern, sidewinder, trilobite, a chiton, an isopod, harvestman, black grouse, ptarmigan, ruffed grouse, jacamar. What is a jacamar? A limpkin, a dewitcher, dugong. I have no idea what most of these are. When am I ever going to have to look and detect and see what these things are? This brings me back to when I was in Spanish class and I learned chicharrones, and I was just like, when am I ever going to use this again? And I never have. Although maybe I need to go visit South America because I hear that they like their chicharrones. Anyway, I'm making all these jokes. All that aside, Feifei Li and her team did an amazing job collecting and hand labeling what nobody else wanted to do back in the day. So that was a lot of work and it was instrumental in helping grow research with machine learning. Let's add MobilenetV2 and the main Python files for staging, and we'll commit it. And we don't want to merge our code into master, but we want it available in case we want to check it out in future, so we'll tag and check out master. YoloV8 is one version in the family of Yolo, which is historically focused on object detection. But as Ultralytics has taken over owning the implementation, they've made integration seamless and have implemented many different tasks, including classification, detection, segmentation, tracking, and pose estimation. We're going to focus on the detection component, which looks for bounding boxes, their labels, and confidences in an image. And for those not familiar, this algorithm does not mean you only live once, like in pop culture where people do really dumb things, but you only look once. It was named that because the other prominent algorithms, like RCNN, which evolved a faster RCNN, had a two-stage detection system that first found ideal places to look, then performed detection, whereas Yolo runs the full pipeline in one shot. And it runs a lot faster, in real time in fact, which is why it's so popular in robotics and autonomous systems. And there's no official paper for YoloV8, so I went through as many sources as I could to compile a thorough explanation of how it worked. When you perform YOLO on an image, you separate the image into a grid where each grid cell performs its own prediction on that cell by using the model. The model is composed of a backbone, which is responsible for extracting features into feature maps at different resolution levels, getting more complex features as you get further into the model. A neck, which isn't explicitly mentioned, but the neck's responsible for connecting the feature maps from the different resolution levels of the backbone to the head, often with pyramids and integrating contextual information. The head is responsible for whatever you're supposed to be predicting. In object detection, we're predicting a bounding box, an object class, and a confidence in that grid cell. We'll first have a probability confidence for which class is most likely in each grid cell, which is thresholded. Then we may detect multiple bounding boxes, so non-maximum suppression is performed to ensure that we have the best bounding box for each object. Let's dive just a little bit deeper into the model. The backbone is CSP DarkNet53. DarkNet is an efficient algorithm with a small memory footprint, though specifically made for object detection and was initially used in YoloV4. CSP stands for Cross-Stage Partial Networks. These networks use a series of splits and merges to help reduce computation and allow for a better gradient flow. Let's look at the blocks. There are a series of convolution and C2F blocks. The convolution blocks have a 2D convolution which extracts features, batch normalization which helps stabilize the data, and a silo activation function which allows the model to learn nonlinear patterns in data.
Because the stride is 2, each convolution results in reducing the image resolution by half, extracting a feature map at 3 different resolution levels, which then connect into the neck. The C2F block has a convolution, split, a series of bottlenecks, concatenation, and another convolution. The bottleneck residual block helps reduce computation, and the C2F block aims to combine the high-level features with contextual information to help improve detection accuracy. In the neck, the feature maps are sent through the SPPF block, which is the spatial pyramid pooling fast block. This speeds up computation by pooling features into a fixed size map. Then it's upsampled and concatenated so we can merge the feature maps at each resolution size. Finally, we have the head, where we define what we're detecting. This algorithm is anchor-free, which means we don't have predefined sizes of bounding box that we're trying to match, and we're looking for the center of the object rather than an offset. It also means that we're going to find fewer boxes before performing non-max suppression, which makes it run faster. We have a detached head, which means the bounding box, detection pipeline, and the classification and confidence pipeline are separate. This does mean they could become misaligned, so we either don't have the same number of boxes and classifications, or there might be some spatial misalignment. So we use the TOOD, Task-Aligned One-Stage Object Detection, Task-Aligned Assigner, which aligns classification and localization, and we compute the alignment score, which considers the classification and IOU score, selects the top K positive samples, and then compute the BCE, binary cross-entropy loss for classification, the CIOU, complete intersection over union, which considers the overlapping area, the distance between the center points, and the aspect ratio, and the DFL, distributional focal loss, which helps focus on misclassified bounding boxes. It's also worth noting that detection is happening at 3 different resolutions, 20 by 20, 40 by 40, and 80 by 80, to optimize the results in finding smaller and larger detections. Let's look at some code that focuses on the Yolo components and skips the data stream for now. So first we import Ultralytics and OpenCV, then we create a model, a Yolo object, and if you don't already have it downloaded, it downloads the model. And this is the part we're skipping, which is just streaming in the image from a camera. And then all you have to do is run the callable function on the image to get a prediction. The part that looks most complicated is for each result, we plot over the existing image, and then we use OpenCV to show. And Ultralytics licensing options, so they either have enterprise, you need to contact them to be able to get pricing. And everything that I'm doing is going to be the AGPL 3.0. It basically just keeps things open source and allows the community to continue to contribute and improve upon the model. And something worth noting is there's different size options to be able to use for the model, which has trade-off of accuracy versus size, and we're using the smallest V8N Nano because we're on the Raspberry Pi, a constrained system. So now let's integrate with the camera data flow and the other sensors. Let's check out master, we'll go to our previous state, we'll create a YoloV8 file and a main.py file, and we'll go ahead and check out a new Yolo branch. Let's import libraries, and then we create a sensor manager object, kind of like camera manager, but now we're managing all of the sensors. And we have functions all over the place, but you'll notice these are all member functions, as you see the self being passed through, which is a reference to the sensor manager itself. In the init function, we set the GPIO mode and set RGB and door sensor GPIO pins. We set RGB to outbound mode and the door sensor pin to inbound mode. And we create the PyCamera2 object, start it streaming, and create the Yolo model object. We have the control LED, clear LED, and doors open functions still. They're member functions, but we're going to clear them for the space for now. We have a start monitoring function with the try except, kind of like start streaming. And inside in the while true, we have a triggered boolean, which checks if a person has been detected or the door is open. We capture the image frame and we call this detect faces function, which returns if we found a person in the stream. In the detect faces function, we pass in the image, we do error handling, and we reduce to 3 channels. Then we call the predict on the Yolo model. And because we've only sent in 1 image, we use the first result, and we check through the boxes they found if a person has been found, and we plot the results. We use OpenCV to display the results, and then we return the boolean of whether we found a person. And then we control the LEDs. So if we found a person, we set LED to blue. If the door's open, we set it to red, and if neither, we set it to green. And then we do some more error checking. If you control C, it closes cleanly. So if we have a separate file, the main.py, then we'll need to import the sensor manager from the YoloV8. And if name equals main, the main entry point, we create the sensor manager object, and we run the start monitoring to be able to get the data flowing. Great, so let's go ahead and add our files to be staged, and then we can commit. Then let's check out master and merge Yolo. Okay, great. So this is perfect for my class. It works, being able to use the Yolo model to be able to detect a person, and this is perfect for a security application. But what happens when I want to recognize my toddler, and only my toddler? Like, I know if I set the system up and it'll trigger an alarm every time a person walks in front of it, that my 9-year-old is just going to do this all day long and drive me nuts. So the models that I'm going to be looking into for trying to differentiate between my toddler and anyone else are a custom-trained YoloV8, custom-trained YoloV9, YoloWorld, and Siamese Network. And now we're going to add in YoloV10 and 11. And I'm going to get a little bit more abstract in a few areas just so we don't take so long, but you'll still understand what I'm doing. Let's step back, and we're going to create a new directory to put everything that we need for the toddler detection comparison algorithms. We need a folder for each algorithm, a data folder, and a utility script folder. Let's copy the code from YoloV8 into YoloWorld, because we're going to base the code off that, just make a few lines of changes, and we're going to rename to YoloWorld. Now let's create a couple of scripts and put them in the utilities, which we'll get to those. Let's check out a compare branch for all the algorithms we're going to compare. So I want to first look into YoloWorld because it's supposed to be like a free text. You put in the text and it tells what to detect. So let's see how it does on toddler. There's only a few lines of code that we need to change going from YoloV8 to YoloWorld. And you can see those here in red. So first we update which model we're going to be using, the YoloV8 World v2. And then we add a line which specifies the classes that we're going to be looking for. That's the text that we're inputting, saying this is the class we want to find. And for us, that's toddler. And then the results, we want to do a .predict, which I think you can actually use this in the YoloV8 version, but the example I found used the callable function. So for YoloWorld, we're going to do .predict. And finally, this is just because I renamed the file that I was running from YoloV8 to YoloWorld because that's what it is. The import then imports from the file YoloWorld at the bottom. So I tried YoloWorld with toddler and it did not work. It did not detect him at all. Is it not detecting you? It's getting you on camera, but it's not putting a box around you. What are you doing, Nick? How are you solving my problem, Nick?
With the box around me.
Are you detected now?
Yeah.
Hey, look, I fixed it, Mom. I got a box around me. Yeah, I was dying. But now I need to look into YoloWorld. Why doesn't it just detect a toddler? I know I wasn't the only one with questions to the limitations of this, because when I went to go see what kind of questions you guys were asking in the comments of the YoloWorld video that Ultralytics put out, I saw Theodore BC was asking, can I just use the text input of big hairy wild bro to detect a bear? Ultralytics claims this is possible, but I'm a little skeptical since it didn't just work on toddler. So let's dive in and try to check out what's actually going on in the algorithm. YoloWorld is a zero-shot open vocabulary model based on YoloV8. This means that rather than only being able to detect one of the classes you've pre-selected and trained on like the traditional models, YoloWorld can take any text as input for what you want to detect. YoloWorld uses an open vocabulary detection method, which leverages a text encoder, CLIP, published by OpenAI, to encode the noun phrases extracted from the input text into embeddings. An embedding is a way we can store multi-dimensional numerical data in place of words, capturing semantic meaning like parts of speech, color, size, shape, type of object, type of action, and much more, in numbers, which work more easily in machine learning models. Each word is represented as a vector, and words with similar semantic meaning would have closer proximity. So, dog might be close to wolf, skiing might be closest to snowboarding, but also relatively close to basketball and soccer because they're all sports, and funny might be close to humorous. The proximity can be measured with cosine similarity, taking the cosine of the angle between the two vectors. Embedding representations are more effective and efficient than one-hot encoding, which stores a 1 for the word in question and a 0 for everything else, and that gets pretty sparse. It's common that embeddings are used in LLM-based models.
CLIP takes in image-text pairs and computes a dense cosine similarity matrix between all image-text combinations, maximizing the similarity between the correct pairs and minimizing the similarity for incorrect pairs using symmetric cross-entropy loss. Models other than YOLO World were having trouble keeping up in real time as they're using large computational detectors or an online text encoder. You can imagine with robots and autonomous systems, if you run too slowly and you miss a detection, what might happen. To improve efficiency during inference, YOLO World added RepVLPan, which connects text and image features by taking in reparameterized text embeddings and allows the encoder to be run offline. The prompt-then-to-text strategy encodes a custom prompt in offline vocabulary embeddings. Then the detector can infer on the fly without needing to re-encode. RepVLPan also takes in the multi-scale image features from the YoloV8 backbone and neck, which we talked about earlier. The RepVLPan really helps fuse the image features and text embeddings. With the feature pyramids with multi-scale image features used in YoloV8, it adds a text-guided CSP layer and image pooling attention to further enhance the interaction between image features and text features. Attention is all you need. The attention mechanism used in the transformer, created by a Google research team, has really revolutionized sequential algorithms like LLMs, influencing what many know AI to be today. It's mathematically allowed the algorithm to find which components of a series you should draw attention to more, or are more important to learn some connections with another series. It does this by computing 3 weight vectors for each, the query, key, and values. The output becomes a weighted sum of the values, and the weight for each value is computed by the compatibility function of the query and the corresponding key. There are a few variations of attention, like the scale dot product attention. When you take the dot product of 2 matrices, you find the similarities, as higher similarities have higher values, and lower similarities have lower values. In the RepVLPan, the text-guided CSP layer injects language information into image features, with the max sigmoid attention after the last dark bottleneck block. Max pooling extracts the most important features from the text, and sigmoid scaling squashes the features between 0 and 1, making them better suited for weighting other features. The weighted text features are applied to the image features, making them more aligned with the semantic context provided by the text. The image pooling attention, on the other hand, enhances the text embeddings with image-aware information. After feature maps are created, attention weights are computed to know where focus should be given within the feature maps, and the weights are used to pool the features, enhancing those that are more important and diminishing those that aren't. Finally, we have the box head, which helps find bounding boxes through regression, and the text contrastive head, which looks for object-text similarity by leveraging the L2 norm and affine transformation to help stabilize the region text training. In the pre-training step, rather than having the label data be just bounding boxes and category labels, they use region text pairs. So the region is now connected to a text, which can be a category name, a noun phrase, or an object description. So we have images and texts as inputs and the predicted bounding boxes as outputs, along with the corresponding object embeddings. During training, they use the mosaic technique where 4 images are overlaid onto one image used to train, where there's a list of all positive nouns associated between all the images and a random selection of negative nouns, or things that aren't there, totaling up to 80 between the two.
Pretty early on, I learned that machine learning models are only about as good as their data. So I got curious.
What data did they use to train CLIP, and does it have any toddlers? CLIP says they trained using 400 million image-text pairs collected from the internet in a dataset they called WIT, or Wikipedia-based image text. They used Wikipedia to curate a dataset with 37.6 million entity-rich image text examples with 11.5 million unique images across 108 Wikipedia languages. So let's look at what Wikipedia has for toddler. I see the developmental picture looks like an alien or a fetus. Their painting has multiple people in the image, so there's no distinction between the adult, the child, and the toddler. And the 2 pictures at the very end focus very close up on the face, so none of these are really good representations of what I'm trying to detect, with most of my toddler's body being the features. When I look up child, which is part of the text description of toddler, there's several pictures that represent what I would want the model to look for, though there's no distinction between my older child and younger. It's hard to tell what went wrong. I'm guessing I would need to extract more data and do some analysis on what the toddler embedding looks like compared to the child and person embedding. But because when I looked at this, training was not an option, and I had no hope that there would be any way to distinguish between my older son and my younger, I decided to cross this off the list and move on. Let's come out of the long-winded tunnel of YOLO World and shift to training each of the YOLO models. But to train, we need data.
And the data sets that I'm going to be collecting, I'm collecting very short data sets because I would rather spend time with my toddler rather than spend time labeling my toddler. Only 2 4-second videos, one of my toddler walking to the bathroom, one of my older son walking to the bathroom, and I'm going to be labeling them in slamivait, which is an online tool that you can use easily and for free if you have a small enough project.
Speaking of data, I want to talk about our sponsor, Storyblocks, a huge provider of data who allows unlimited downloads of diverse and high-quality media at one predictable subscription cost. They have everything you need in one place: 4K and HD video, images, music, and sound effects, and templates with a monthly or annual plan with no hidden fees. I use them throughout this video to really enhance the quality of my production, turning what might have been a really boring tech tutorial into a really entertaining one. And the best part is, when I use their content, I don't have to worry about the copyright. And they're not just for content creation. They now have a new offering that licenses data to be able to be used in machine learning models. I've had a number of tasks at work that I needed to solve, but wondered, where am I going to find the data? And if I find it online, is that legal or ethical to use? Storyblocks has that covered too. So however you need to use their content, to get started with Storyblocks, head to storyblocks.com/CarissaStisser or click on the link below in the description. Next, let's go into data, create a train, validate, and test directory. And we're going to put the MP4s we're going to use in each of those. Now we have the Nick and Nelson, just them walking to the bathroom and train. But I wanted to have a little bit of variation in validate and test. Like sometimes my kid will wear a dinosaur hat or a superhero mask. And I wanted to see how the algorithms might be able to perform on a little bit different data. Now remember, the train is used in training the model, validate is used in evaluating the model, and we're going to iterate through this process, updating the hyperparameters to be able to get an improved model. Then we use the test data as brand new data to see how it's actually performing and compare between each of the different models. Let's jump into the train folder and let's see what process we're going to do on each of the MP4s. So first we run the Python script video to images, which breaks down an MP4 into each of the JPEGs, which have each image frame, with an incrementing naming convention. Then we'll download CVAT data, which gives each of these frame TXT files. An example in the orange box has 0 for the toddler type, and then each of the next 4 values are the min and max X and Y values for the bounding box. But the problem is the frame doesn't match with the name of the JPEG, so we need to run the script fixNaming.py so that we can have each of the JPEGs and the TXT files matching the naming convention so that we can have multiple videos broken out in each of the train, test, and validate folders. Now jumping into YoloV8, we need the train.py file, which we're going to use for training the model. We also need the YoloV8.yaml file, which tells the train file where to look for each of the datasets, and it breaks down the names of the different types of classes. We're just using 0 for toddler. So let's look into the code. It only takes 4 lines of code to train a YOLO model, which is insane. First, we import libraries, then we create the model, sending in the YAML file, which tells it where the data is and what to detect, and we load in the pre-trained weights. Then, the meat and the potatoes, we run the train function, which trains the model using whatever hyperparameters and data augmentation parameters that we send in. We're going to be updating those to try to improve the model. Next, we currently have it commented out, but we export the model once it's the optimal model we want to save. So we'll remove the comment when we have the optimal model. So I go ahead and run this so that we have a baseline, all right? So using the mean average precision at 0.5, our baseline is 0.801. And it took about 10 minutes to run for 100 epochs. So we're going to keep anything that improves it, and we're going to remove any parameter changes that makes it worse. This is the precision recall curve as our results for running our baseline. On the right, you can see a perfect precision recall curve as the box. To understand it completely, let's look at the confusion matrix. We have true positive, which is something that you detected, that you should have detected, that was labeled, that's good. A true negative, you did not detect it, and there's nothing there, you shouldn't have. A false positive is when you detect it, but you should not have detected it, there's no label. A false negative is when you should have detected it, but you didn't, there is a label. So the precision is how much did you detect out of what you should have detected, and recall is how much did you detect without detecting too much extra stuff, right? There's a trade-off. So that's why we have the precision recall curve. When we combine it all, we use that to make the equation for the mean average precision. The mean average precision is the area under the precision recall curve. The calculation uses an average of all of the classes, but we're only using the toddler class. So instead of the average of all the classes, we just reduce it to the average precision just for toddler. Now, when we're doing object detection bounding boxes, we need to consider the IOU, the intersection over union, the intersection of the label and the prediction over the union of the label and the prediction. And our threshold is 0.5. Anything above that is a true positive. Anything below that is a false positive. So first we run with dropout, which helps remove dependencies on certain features, but that had a worse result at map of 0.683, so we remove it. Next, I tried the full image size because we were running with half, but that had a CUDA memory error, so we don't keep that change. Next, I tried using the pre-trained weights, and that had an improvement. So we have map at 0.809. I'll go ahead and keep that. And then I try the cosine learning rate change, which had a worse change, so I remove it. Then I try updating the degrees for data augmentation, and that did not improve. So I removed that. Here's some of the data that I tried training with, but you can see that wouldn't be realistic. Next, I tried changing the scale for data augmentation, but that didn't have any improvement. Here's some of the data. So I go and remove that. Next, I tried reducing the learning rate to 0.001, and that had an improved map at 0.859, so we'll go ahead and keep that. Next, the hue, I changed increasing the hue variation for data augmentation, and that had an improvement. You can see with no IR camera data that makes sense that it's better represented. So I tried increasing it more to 0.5, and that still had an improvement at 0.922 map. But at 0.8 increase, it did not have an improvement, so I kept the 0.5. Next, I tried variation on saturation, and that did not have an improvement, so I got rid of that. Here's the data. Next, I tried increasing the epochs, and that did not have an improvement. So I went ahead and kept the hue at 0.5. That was the best result with a map at 0.922. Here's the precision recall curve. It's pretty darn good. Here's the results. We can see that as the loss is decreasing over time, we never stagnate. Finally, I remove the comment. I go ahead and export, and we can use this model when we want to be able to compare. YoloV9 was based on YoloV7, which was based on YoloV4. YoloV7 interestingly came before YoloV6, and let me tell you, the most hilarious paper of the bunch was YoloV3, where Joseph Redman, the original creator of Yolo, was quite colloquial and made it clear he was done supporting the Yolo algorithm. There's so much snark in his paper. Can you cite your own paper? Guess who's gonna try? This guy. Just go read the paper if you want to laugh. This did give me a bit of a vibe of the Weasleys leaving Hogwarts early with a bang when they disapproved of Umbridge's actions. Thumbs up if you get the joke. Anyway, we're going to avoid the rabbit hole of going through the full Yolo saga and just focus on YoloV9. In this paper, the authors focus on the bottleneck principle, which is that you can lose data through any function, and you often lose data through neural networks. While a few other methods try to tackle this, there are always drawbacks. The authors propose using Programmable Gradient Information, PGI, which consists of a main branch, an auxiliary reversible branch, and multi-level auxiliary information. The inference uses only the main branch, so there's no additional inference cost. The auxiliary reversible branch can choose any reversible architecture, and it helps generate reliable gradients through additional pathways. Multi-level auxiliary information helps connect the feature pyramid hierarchy layers of auxiliary supervision, and the main branch to combine return gradients from multiple different prediction heads, which can be used to update the parameters. They program the gradient information propagation at different semantic levels, and can avoid semantic loss, helping handle error accumulation. There's no restriction on size or depth of neural network this can be applied to. And the reversible architecture of PGI is built on the auxiliary branch, so there's no additional cost. The second focus and innovation of this paper was their new backbone GLAN, or Generalized Efficient Layer Aggregation Network, which is a framework that promotes quick inference. The same authors had created the original ELAN in their paper, Designing Network Design Strategies through Gradient Path Analysis, and elaborated in YoloV7 with extended ELAN. GLAN is a combination of ELAN and CSPNet. CSPNet improves inference by reducing redundantly learned gradients, while ELAN focuses on inference speed optimizations. GLAN fits the new PGI framework, which allows the model to be able to learn from the data more effectively, and is built flexibly to be able to handle other processing blocks. Spatial pyramid pooling is used with ELAN to help capture multi-scale feature information. Similarly to YoloV7, YoloV9 uses an auxiliary branch component in the head, which captures and retains gradient information during training, helping the main branch more quickly learn what it needs to learn. Let's copy the YoloV8 files as a base, and while we're at it, let's add in folders for YoloV10 and 11 and do the same for them. Now we're going to go ahead and train a YoloV9 model, which is basically the same code as YoloV8, except now we're leveraging the YoloV9 YAML and YoloV9 pre-trained model. This is the baseline map of 0.5. We have a starting map at 0.359, which is pretty darn bad, and it's worth noting it took 50 minutes to run 100 epochs. That's 5 times longer than it took to run YoloV8, so this was much more painful in the training process. And it's worth noting that I had to reduce the batch size to 4 to eliminate the CUDA memory error. Here are the initial training results. The precision recall curve is really bad. And so first I tried pre-trained, and that has a worse result of 0.303, so I removed that. Then I go ahead and try using the cosine learning rate, and that had an even worse result at 0.253, so I removed that. Next, I tried increasing the degree variation, and that had an improved result of 0.36, so I keep it. And then I try reducing the scale to 0.3, and that had a better result, so we keep that. Here's some of the data. Precision recall curve getting a little better. Then I go ahead and reduce the learning rate to 0.001, and that had a really huge impact at 0.847 map. So here's the precision recall curve, getting even better. And then I go ahead and try to update the hue variation, and that had a worse result. So we go ahead and get rid of that. And here's some of the data that came out of that training set. I reduced the learning rate even more to 0.0001, and that had an even better result to 0.93 map. So here's the results there, and precision recall curve's getting even better. Now I go ahead and up the epochs to 500 just to see if I can get any better result by having it run longer. And that has the 0.95, that is a really good result. Precision recall curve's looking great. On to YoloV10. YoloV9 was only around about 8 months before YoloV10 was introduced by a Chinese group at Tsinghua University. They again focus on performance improvements based on YoloV8, reducing redundant computations and removing non-max suppression, which has been present from the beginning. Because Yolo is structured to have one-to-many detection strategy, there's one object and several positive predictions exist. Non-max suppression has been necessary to reduce those predictions down to the one optimal choice. Instead, they decide to use a hybrid approach in their dual label assignment. They use a one-to-one matching strategy, which alone would have weak supervision, which leads to lower accuracy and convergence speed, but doesn't need non-max suppression. But they add in a one-to-many, which provides a richer supervision and helps inform the neck and backbone for improved results. The one-to-many head is discarded during inference, so it doesn't add any inference cost. To improve performance, they use a lighter weight classification head, create more efficient downsampling by decoupling the spatial reduction and channel increase operations during the standard two-stride convolutions, and use a rank-guided block design, decreasing complexity of stages that seem to hold redundant data rather than using the same block design everywhere. Next, they focus on accuracy improvements. First, they increase the kernel size from 3x3 to 7x7 at lower levels to increase the receptive field as they can, avoiding contamination at the shallower levels, which would affect detecting small objects. Next, while self-attention has high computational complexity and memory footprint, they establish a partial self-attention module, which is comprised of a multi-head self-attention module and a feed-forward network, and only used after stage 4, with the lowest resolution to reduce computation. Let's train the model. I run this command to update Ultralytics to gain access to YoloV10, and now that we're this far into the video and probably delirious, I'm going a little faster and adding an element of fun in just a sec. So first we have our train.py file, which looks very similar to YoloV9. It finds the custom data in class we want to detect in the YAML we've created. And here's the fun. I'll present the parameter variations just like an auction house, because why not? We keep the parameters that improve and get rid of the parameters that do not, so setting pre-trained equals true made it better, cosine LR equals true made it worse, increasing degree augmentation to 15 made it better, increasing to 25 made it worse, tried scale augmentation at 0.3 and that made it worse, reducing the initial learning rate to 0.001 made it better, but reducing by a factor of 10 made it worse, trying to increase the scale augmentation to 0.3 made it better, trying to add a hue data augmentation made it worse, changing momentum made it worse, adding in a dropout element, kept it the same but we kept that. Then I tried running at 1000 epochs, which made it worse, but I noticed it was petering out at 200 epochs, so that was our final winner at 0.913 map. And this is why I'll never be an auctioneer. Although I do kind of sound like a baseball player. Hey, batter, 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 swing, batter, 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 batter. Anyway, YoloV11.
So while I was reading this paper, I got this thought.
You know how some hotels really go the extra mile to try to make your stay at their hotel an incredible experience? Silky sheets, a chocolate on the pillow, a nice restaurant, incredible views, the works. Well, I felt like this paper went the extra mile to make this a positive reading experience by first including a chart of historical data on all the previous Yolo models, which I'm sure anyone that hasn't been around from the beginning really appreciates. They included current events. Apparently, Yolo had a conference in 2024 hosted by Ultralytics that you could join digitally for free. And this Yolo ensured they focused on including all tasks, including object detection, instant segmentation, image classification, pose estimation, oriented object detection, and object tracking. And I hadn't even gotten to their algorithm yet. So again, they focused on increased accuracy and efficiency, building on YoloV8, while keeping in mind all tasks they now support. One thing worth noting, because there's such rapid development in Yolo models, they're not able to simply build one on top of another, but they're skipping over the latest advancements in the most recent model. But if they went back, another model might come out before they can publish. One key advancement in Yolo 11 is the C3K2 block, which replaces the former C2F block in many cases, and is a more computationally efficient version of the CSP bottleneck. It uses 2 smaller convolutions instead of 1 large one, and it uses a faster, smaller kernel size. Depending on what input parameters are given, the C3K2 can use the standard bottleneck structure, or it can extract deeper, more complex features with the C3 module. It also allows flexibility by allowing customizable kernel sizes. The C3K2 block is used along with convolutions in the backbone, which supports building feature maps to extract features at multiple scales. At the end of this pipeline, they use the spatial pyramid pooling fast block from previous models to aggregate the information between convolutional and fully connected layers, allowing the backbone to learn faster. After the SPPF block, they introduce a new block, the C2PSA, or cross-stage partial with spatial attention. This enhances the spatial attention in the feature maps, allowing the model to focus on more important regions within the image, resulting in improved accuracy. The C3K2 block is also used in the neck, which helps aggregate the features using upsampling and concatenation of different feature maps at different resolution levels to pass on to the head. In the head, there are several CBS or convolutional batch norm silo blocks, which help refine the data by extracting relevant features, stabilizing and normalizing the data flow through batch normalization, and using silo activation function to support nonlinearity, improving model performance. The head varies based on the task at hand, but object detection has the set of con 2D layers to reduce the features to the number of outputs needed for the bounding box coordinates and class prediction. Ultimately, for each object, we're still getting a bounding box, an objectness score, which gives us the confidence, and a class score, which helps determine the class. Yolo 11 had the exact same code as Yolo 10 for its train and YAML files, except for changing out the 10 for 11. Again, we're going to keep the parameters that improve the map and get rid of what makes it worse. And it's worth noting it took about 10.5 minutes to train 100 epochs. So, pre-trained equals true, kept it the same, but we're going to keep it. The cosine learning rate made it better. Increasing data augmentation for degrees made it worse. Increasing data augmentation by adding the scale equals 0.3, that made it better. Reducing the learning rate to 0.001 made it better. Reducing by another factor of 10 made it worse. Adding hue augmentation made it worse. Changing the momentum made it worse. Adding a dropout kept it the same, but we're going to keep it. And I tried 1,000 epochs again, which made it worse. And there's the results. And we landed at 0.92 map, with the parameters I used in the train.py. The one thing I was curious to hear back from anyone who regularly trains detection models is, what's your standard for labeling data when it's cropped? Like, in this series of data, most are nicely labeled, but in the upper left there's only a sliver of my kid. So would you label this? I wouldn't get mad at the model if it didn't get it, but right now it just shows in the overall performance of the numbers. One of these things is not like the others. Yeah, that was not my plan, but sometimes new algorithms come out and you gotta roll with it. A Siamese network is where you have 2 identical parallel convolutional neural networks structured so the network can learn similarity by optimizing a rank loss function, rather than classifying or detecting something. A common application of this would be a security entrance, where you have images of all of your employees, and to gain entry, their face has to have a high enough similarity to what the model has learned of their face based on an acceptable threshold. Let's break this down into the main components. First, we have the data, which is separated into one folder for each class, but we create triplets of data to train the model. This triplet consists of an anchor image, a positive image, and a negative image, where the anchor and positive must have the same class and the negative must be a different class. Second, we have the model, where feature extraction is performed, and an embedding is made out of the image. Next, we have a contrastive loss function to help the model learn to prioritize parameters that create embeddings that produce a smaller distance between similar class types and a larger distance between different class types. Next, we have the training module, where we use different hyperparameters like the number of epochs, learning rate, and distance threshold to train the model. Finally, we have the plotting and data analysis, so we can make better choices of how we train the network. Let's look at the high-level view of how this translates to the coding architecture, as this model's implementation was much more complicated than the Yolo implementation, but with 4 lines of code, basically everything is. I like to keep functionality separate for each class, so the main function creates a model trainer class, which can train or evaluate. When training, it iterates through each epoch, feeding the data through the model, and uses a loss function to optimize the embedding parameters. This highlights that the model trainer has both the Siamese Network class, which defines the model for feature extraction and embedding creation, and is inherited from the parent class, and n.module from PyTorch, and it has a triplet loss class, which defines the loss function used while training. I have a data reader class inherited from PyTorch's utils dataset, which handles reading in and arranging the data that gets sent through the model or the evaluator. The evaluator has a visualizer class, which helps create evaluation plots. I also have a logger to write the progress and results to a results.txt file, and save useful plots to a certain directory within a runs folder for that run. I made this a singleton, which is a design pattern that allows more than one source to use the same instance, so there's no fighting over the write function, though I do lock it down to avoid multiple threads from accessing it at the same time. Now, let's dive into the code. Let's start with the main and model trainer. In the main, we import the model trainer, create a model trainer class, and call the train function. In the model trainer, we import the necessary libraries, define the class and constructor where we take in the file paths for train, validate, test data in the anchor image, define if we're in test mode, and state if we want to record the run through logging. We define the epochs and distance threshold, create the logger, Siamese network model, triplet loss, and define our atom optimizer. We'll set up the logger if running in record mode. Then we read in the training and validation data by creating our own Siamese datasets, and transform the anchor image so it's usable, setting to CUDA memory. If we're in test mode or in inference mode, we read in the already trained model, set it to evaluation mode, get the embedding of the anchor, and read in the test data. I'm running slightly different code for running straight on the Pi that's been integrated with the streaming camera, rather than pre-recorded data. Continuing with the model trainer class, we have the print and write function, which takes a string that both gets printed to the console and gets written to the results file with the logger. I also have a run inference function, which takes in an image. We don't change the gradients to the model. We get the anchor embedding and the image embedding, take the Euclidean distance, and return whether it's within the threshold to be considered similar to the anchor. Next, for the train function of the model trainer, we loop over the epochs for each training iteration and call train. I loop through each triplet, setting the data to CUDA, sending it through a forward pass through the model, computing the loss, sending it through a backwards pass, and recording the epoch, loss, and triplet. Then we save off the model, evaluate the performance on the validation dataset, record the time it took to train, and visualize results. And in the evaluation function, we loop through the validation dataset, recording the true positives for the NIC images and false positives for the Nelson and empty images, compute our average precision, and record the data. Let's look at the data reader next. I import the libraries, then create the Siamese dataset class, inheriting the PyTorch utils dataset parent. In the constructor, I'm initializing the parent, recording my incoming parameters, establish my image transform to put each image in the right format for the model, and then prompt reading in the data. The read in data function creates a vector for each NIC, Nelson, and empty, then loops through the file system, and depending on whether we found a JPEG image in the NIC folder, Nelson folder, or empty folder, we open, transform the image, and save it to the appropriate vector. Then we create and store the triplets, looping through the NIC files to establish each as an equally contributing anchor. Then we randomly select a corresponding positive and negative image, and append it to the triplet vector. And because we've inherited our Siamese dataset from the PyTorch dataset, we include a definition for the parent's function of getting the length and the item by index from our created triplets. Next, we'll look at the Siamese network class where we create the model. We import the libraries, then create the Siamese network class with constructor. Because we're inheriting from the nn.module parent, we initialize the parent. Then we bring in the resonant model, where PyTorch is doing the heavy lifting, having to find the model in the library. I reset the final layer to be compatible with what we're trying to find, and freeze the early layers to leverage what they've already learned. Finally, I create my forward pass functions, one to handle one image and one to handle the anchor positive and negative images all at the same time. Let's look at the triplet loss function. First, I import libraries, then I create the triplet loss class, inheriting the nn.module, and initializing it, and saving off parameters. Then I bring in PyTorch's triplet margin loss, and I create a backwards and forward function to work with the training process. Now we'll look at the visualizer, where we import our many libraries, create the visualizer class and its constructor, where we're passing in and saving an instance of the model, the validation data, the anchor embedding, and the run folder, so we can save off our images. We also initialize the logger here, and we have a print and write function where I print to the console and record incoming string to the results log. I have an evaluate distance threshold function, where I create an embedding of each validation image from the model, compute the distance between it and the anchor embedding, and scatter plot it so I can see the distance difference between Nick, Nelson, and empty images. I give each different Y value so I can see them separately on their own lines, and I save the image in the run directory for this run. I also have a visualize embeddings function where I create a plot to visualize the PCA and T-SNE and distances all in one. For each Nick, Nelson, and empty images, I get an embedding, compute the distance between it and the anchor embedding, and append the data to the respective vectors. Then I reshape the data so I can perform PCA and T-SNE, and then I plot and save off the image in the run folder. Finally, we have the logger, which has an interesting construction as it's a singleton. After importing libraries, we create the logger class and overwrite the new function, which is generally called behind the scenes before the construction to instantiate the new object. But it'll now run what we write instead, which is to check if an object has already been created for the class, and if it has, use that same object, otherwise create a new object. This ensures there's only one logger class being used between any of the other classes that want to use it. In the constructor, we save off the base path in the log and establish a threading lock. In our setup function, we create a runs folder if it doesn't exist, and create a folder for the current run based on the date time. We also open the results file to write to. And that's all in a try-catch block to catch any errors. We have a write function, which puts a lock on it, so no one else can write at the same time, and it releases naturally after. There's a function that can return the run folder, and the final function is ensuring we close the file on the destruction of the class. Now let's look at the training. First, we have the data. I separated my data into Nick, Nelson, and empty because I want to be able to easily plot the difference between the three, even though I'm trying to detect Nick, or toddler, versus the other two. When I pass the data through, I'm sending it in triplets, one anchor, one positive example, and one negative example. Next, for the model, I'm using ResNet, the residual neural network for feature extraction. I started with a series of convolutions, ReLU, max pooling, and batch normalization, but I moved to using ResNet as it was a better feature extractor. It uses skip connections to jump over layers in the network so it can learn with great depth. Next, I'm using a triplet contrastive loss function which optimizes to have a distance between similar types and different types be of at least a certain margin parameter. Here's where we define the similarity metric. I varied between the Euclidean distance, which is just the distance between the 2 points, and the cosine similarity function, which measures the similarity between the cosine of the angle between the vectors, or the dot product of the vectors divided by the product of their lengths. This only depends on the angle of the vectors, not on their magnitude. So in the training, I iterate over my epochs, feed my triplet datasets through the model, and allow the model to update its parameters to improve performance based on the triplet loss and the atom optimizer, printing the updated loss at each epoch, and I ultimately save off the model in the end. I also have an evaluation path to send new data through the model, so on each training iteration, I send the validation data through the trained model to see how it performs. The test data I'm saving until the end to be able to compare it to the other models. And because we're not detecting a bounding box, we don't have to consider the IOU, but we're still using the average precision for toddler class. In my results, at first I was getting 0 predictions, so I started analyzing and plotting the distances, and found that I needed to increase the thresholds. So I played around with both the margin, which helps the loss determine how far apart the different classes should be, and the distance threshold, which helps decide whether it's close enough to be considered similar. I started seeing some results around 120 for both. I also wanted to see if I sent data through after the model was trained, if it seemed clusterable, which to me means the model can learn and predict well. But because an embedding is 128 dimensions, in this case I needed to use dimensionality reduction algorithms, like PCA, or principal component analysis, where the eigenvalues and vectors of the covariance matrix are computed to get the principal components, taking the data with more impact on the variance, which I reduced to 2 dimensions. I also use T-SNE, or T-distributed stochastic neighbor embedding, which is a nonlinear dimensionality reduction technique that uses the global covariance matrix to reduce data in an iterative process. It can also be used to visualize feature maps from CNNs. The results looked interesting, but it didn't seem easily clusterable, so I improved the feature extractor from a simpler CNN to use ResNet. I tried reducing the learning rate from 1e to the -3 to 1e to the -4, but this made it worse. I played around with the loss function's distance metric between a manual pairwise distance function and PyTorch's triplet margin loss, which did better. I also compared the distance evaluation between cosine similarity and Euclidean, which Euclidean performed better. I had started at 16 epochs, but noticed the loss was stagnating at 0 around 9 epochs, so I updated it to stop at 9, which took between 12 and 30 minutes for each iteration, until I decided to play around with the data. When I first loaded in every possible image and created every possible triplet variation with every negative image, it took way too long to create. And because all of the data is from 2 video sequences, most of the adjacent images have very little difference between each other, so I decided to skip some to speed the training process along, only taking 1 out of every 15 frames, and at 24 frames per second, this would be about every 3/4 of a second. Although after running for a bit, I was realizing the data was not balanced. I had 48 positive images and 238 negative images, so I took every 5th positive image and every 15th negative. But after a while, I realized I'm not permitting much variation, so instead I used a similar total of 75-20 triplet sets, looped through each positive to create an anchor, and randomly chose each other positive and negative, ensuring the positive was not the same image. I had tried using data augmentation when the loops were in place with rotation, color variation, affine transformation, and resized crop, but that increased to 8 times the data and took 4 hours to train, and created a worse result, so I moved off of it. I did try using several different anchor images. Actually, a lot of thought in industry has gone into choosing an anchor. Choosing a hard anchor means the embedding distance between the negative example and the anchor is not very large, or in human terms, it's hard for the model to tell the difference between the negative and the anchor. If you choose this route, the model might converge more quickly, and the model can sharpen the decision boundary between classes, but there's also risk of overfitting and a noisy gradient. Choosing a medium anchor is not as difficult as a hard anchor at determining the difference, though there is still a reasonable challenge. When you use a medium anchor, there's a balance between easy and hard, so it helps avoid negatives of hard like overfitting and noisy gradient, but it still helps prompt the model to learn a broader variety of cases. But it may be slower to converge. If using a soft anchor, it's relatively easy for the model to distinguish between the anchor and the negative image, and it makes it easy for the model to find patterns and relationships in the data and avoid the risk of noisy gradients or unstable training. Though if only using soft anchors, the model might become too simplistic and fail to generalize to harder examples. To be honest, with only 48 images to choose from in the same video sequence, I really just experimented with several different images being the anchor and stuck with the one that seemed to perform better than the others. I froze the early layers in the model, leveraging more of the pre-trained data. I did make another discovery when looking at the average precision calculation I was making. Online, I found the calculation to be true positive over true positive plus false positive. But when seeing the results were fairly low, I realized my validation dataset had 169 positive images and 403 negatives, and I was very frequently getting more false positives than true positives. But that makes sense when there's 2 to 3 times more data, so I normalized it, dividing the true positives by 169 and false positives by 403. And that raised the results significantly. Looking back, I'm sure I should have done this from the beginning, but because Yolo handles the calculations for you, you don't have to think about it. I played around a bit more with the thresholds and epochs. After a few days of training, I ended up with a 1.0 average precision, running 9 epochs, 74/88 triplets, with positive and negative chosen randomly, a distance threshold of 120, a margin of 120, a learning rate of 1e to the negative 3, and the triplet margin loss function. Looking at the plots, there's still some overlap, but you can see more separation. This whole journey kind of felt like I was whitewater rafting, where at first I really didn't have any clear path on what to do, sometimes getting trampled along the way, but as I kept pushing through, trying things out, somehow I made it out okay in the end. But if you would have done anything differently, note it in the comments below. I'm always open to learning.
Now that we're done with the code, let's CD back to the toddler compare and make sure our .gitignore includes files we don't want to commit, like the runs directory, the data directory, or anything with a model extension. Often models will be tracked separately as they have a larger file size. And let's add all files to be staged that aren't ignored. We'll commit it and merge compare back to master. Now for the results. We're going to test each of these models on new data that we've never seen before. Now keep in mind, these are going to be as good as the amount of time that I was willing to put into it, like 1 or 2 days of training for each model. And if you're a professional, you're really going to dive a lot deeper and try to squeeze as much as you can out of each model. So we have YoloV8 through 11 and the Siamese Network. I noted the training maps we got for the validation data just for reference. I also noted the training time. YoloV8, 10, and 11 were pretty close, between 10 and 13 minutes for every 100 epochs, so it was fairly painless. YoloV9 was painful, 50 minutes for every 100 epochs. This means this must be perfection in accuracy to choose this. Probation 9. And Siamese really varied. It was medium painful,
comparable to the painless algorithms when it had less data, but as soon as you added data augmentation and more resolution to images, it could be as painful as 9. So we're going to look at 3 factors: speed, compute, and accuracy. For speed, we're looking at inference speed. YoloV8 and 10 both run at 0.4 milliseconds, and 11 is slightly faster at 0.35 milliseconds. Both are fast enough. 9 is much slower at 24.3 milliseconds, but the Siamese network runs at 2.5 seconds, not milliseconds, seconds. And that's really just not fast enough to keep up with the camera and be sure I'll make the detection. So, Siamese is out.
So now let's talk about compute. There's kind of 2 different ways you can look at compute when you're talking about algorithms. One is the academic approach, which is big O.
Big O you learn when studying computer science. It's a method of expressing how much time complexity an algorithm has in the worst case scenario. A for loop, when looping through every item, is O of n. A nested for loop is O of n squared, as it loops through every item n times n times. Binary search is O of log n, as it eliminates half of the elements to loop through each time. And an algorithm like merge sort is O of n log n, as it has a divide and conquer approach.
This would take forever to figure out. It's horribly complex and utterly useless to me because honestly what I want to do is look at the Raspberry Pi 4 and see how many cores does each algorithm actually take, and I have a much easier way to do that.
When I run htop in a command line, I get this. In the upper left, there are 4 rows of vertical bars which show what percentage of each of the 4 cores are being used on the Raspberry Pi 4. On other devices, this will likely have more cores. Below that, you can see the memory usage. If that's going up and never coming down, you probably have a memory leak. And the lines below the green bar show each of the active threads, starting with the threads using the most CPU in order by percentage. And yes, it can go over 100%. This one goes up to 400% because there's 4 cores, 100% each. So I don't have a great way of getting a precise number. If you do, note it in the comments, but all the Yolo models look pretty similar. Maxed out completely, 3 cores staying at 100%, and 1 in the 90s. But they don't crash. The Siamese network, which was already knocked out, was most of the way maxed out, but had more compute leeway than Yolo. And finally, the map, or average precision. These results were insanely close. Siamese had the lowest, though I feel like there were so many options to experiment. Given more time, it also had more options for things that could vary in training. But it's not fast enough, so it doesn't matter. YoloV10 did the worst, but not by much. Our first place winner was YoloV8 by 0.001 map of 0.893. YoloV9 came in next, but honestly, if I were working with this over a period, I probably would have just kept YoloV11 at only 0.001 under V9, but with much faster training cycles. And if I wanted to be extra sure I wasn't getting too many detections on my older son, I could use a slight hack. As we know we're in a fixed space in orientation, I can just filter out anything with a bounding box too tall. Let's get YoloV8 up and running on the board.
So it's complete, we've picked our best one, and we're ready to test on the real world. Now, let's see how it goes. Wait, no, stop! This far, you are amazing and a truly passionate learner, I can tell. So consider hitting the like and subscribe and the notifications button. I've got a few coming up that are going to be really good. And consider joining my Patreon where you can be part of my network, see sneak peeks and what I'm working on next.